So this is chapter 6, section 3, number 17. And it says, use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves about the specified axis. So the one we have is y equals to 4x minus x squared, and it's to rotate it about the line y equals to 3. Oh, no. This is so these are the two functions, this function, and it says rotate about the line x equals to 1. Okay, so we have a nice parabola, and then we have a nice line at y equals to 3. So, this guy we can move around a little bit. Let's see, that's just going to be negative x squared plus 4x. Okay, so it's going to be a parabola, and it's going to be flipped upside down like a sad face. Let's factor out an x. That's going to be, let's factor out the minus x. It's going to give us x minus 4. So one of the intercepts is going to come at 0, right? So if we want to figure out the x intercepts, we have them at 0 equals negative x minus 4. So that means that one of them is at x equals to 0 as one of the intercepts. And the other intercept is going to come at x minus 4 equals 0. So x equals to 4 is the other intercept point. Let's double check that. If we put a 4 into here, that's going to be 16, negative 16. And then we put a 4 in here, we get positive 16. So it checks out, right? Those are the two x-intercept points. And then the vertex that we have y equals to ax squared plus bx plus c. If we had any quadratic that fits this form, the vertex is, I said the x-coordinate. The x-coordinate of the vertex is going to be the value negative b over twice a. Right? That'll give you the x-coordinate of our vertex. So in our little scenario, we had negative x squared plus 4x. That means that the a is a 1, the b is a 4, and the c, well, it's 0, right? We can always throw in a plus 0 here, plus 0. And so that means that the x-coordinate of our vertex, x-coordinate of vertex, is going to be equal to negative 4 divided by twice a. Oh, the a is a negative 1. Oops. Correction here. The a is a negative 1, not a 1. So then that means that this is a negative 1. That's important because I need them to cancel. So that'll be negative 4 divided by, that'll be negative 4 divided by negative 2, which gives us positive 2. Okay, the x-coordinate of my vertex is a positive 2. Now that I have my x-coordinate, well, to find my y-coordinate, I evaluate the function at 2, right? So I just got to plug in 2 into my equation, and it's negative something squared plus 4 times something, and I'm going to plug in that 2 and 2. So I get that this is negative 4 plus 8 or just 4. Okay, so I have my x-coordinate of my vertex, I have my y-coordinate of my vertex, so the vertex is at the point 2, 4. Okay, whole lot of work just to figure that out. And now I can bring that all together and just kind of rough sketch this thing. I know it's a parabola. I know it opens upside down because this term is negative. And so it has an x-coordinate there. It goes up, so it's going to come up like this. Come back down and go this way. So it goes through the point 0, 0. It goes through the point 4, 0. And it's got a vertex up here at the point 2, 4. Okay, so that's all and everything we ever wanted to know about the first function y, which is equal to negative x squared plus 4x. Okay, so we got all the important pieces of information. Now the other equation we're dealing with is the equation y equals to 3. Well, that's just going to be a nice straight line that goes this way. Let's see. This reaches a height of 4, so say somewhere around here is the line y equals to 3. Obviously, it goes right through there at the point 0, 3. But I'm not sure what that is. I'll have to figure that out. And I'm not sure what that is. I'll have to figure that out. That might become important. So let's leave that on hold for a second. And now it says to rotate about the line x equals to 1. Okay, x equals to 1 is going to be a vertical line. All right, well, let's figure out what happens when you plug in a 1 into our function, into this function. So let's see. When x equals 1, we have y equals to negative blank squared plus 4 blank. Right, so we're putting in a 1 in there, 1 there, 1 there. That's going to be a 3. Ah, how convenient. Things work out really nicely. This is going to be negative 1 plus 4, which equals to 3. Just as I had suspected, they're not that cruel. This is a nice, easy number. It's the number 1, 3. 1 and 3. 1, 3. Okay, and that happens to be the axes by which we want to rotate this. So then this line that comes this way is the line x equals to 1. So we want to rotate around this one, right? Rotate around this line like this. If we rotate around this line, we're going to get something that kind of looks like that bun cake again, right? Hopefully we can visualize that. Let me see if I can somewhat kind of draw that. Boy. So if we rotate around it, it's going to be something that looks like this. Oh, that's ugly. Already messed up. This. That. And it's got kind of a melon-shaped thing. Something like that. And then this is kind of rotating. Kind of like that. Oh wow, that's really ugly. Okay, well, let's go over technology. Alright, so let me see if I can get a better looking graph. By the way, if you want to check this out, here's the address for it. So it's a public thing. All right, let's see if we can get some help with this thing. So I'm going to do method of shell.
Do we have to register to use that calculator, the GeoGebra? Because I have a hard time getting it to display the way you have it on your screen.
Yeah, I'm not registered, but you're right that it's not very user friendly. There's all kinds of things that, you know, cause problems. And in fact, I think right now it's not responding. So, uh,
Yeah, it's like the beta mode, right? So you have to keep selecting disks or horizontal axis in order to display the thing you want when you graph it for the function.
oh, there we go. I don't know what it is, to be honest. Sometimes sometimes it just stops working. Sometimes I don't know what it is. So it's not foolproof. But let's see what this does. Okay, so let's see if this will look good. We had this equation was -1 times parentheses x to the second power close parentheses, just to make sure there's no mistakes there, plus 4x. So hopefully that looks okay. And then the other one is y equals 3. Okay, so let's zoom out. Okay, that looks good. So we have the parabola and we have this line, but now we have to make sure we go to the region that we're interested in. So we know that we want from here to here, so we want A to run from 1 and then, good. And then B, let's see, is it 3? There we go. Okay. So here's that parabola. And then we have the y equals to 3. So we have our little zone in between. And we did a little, well, I guessed that it was an easy answer, and it was 1 equals to 3. Otherwise, to solve it, you're going to have to set this equal to 3 and figure out when does that happen. Right? Let's do that real quick. So I just guessed that at x equals to 1, good things were going to happen. But the other thing you could do to figure out when these two things are true, when is it true? When is it true that this parabola gives you a height of 3? Well, we have to set it equal to 3. So you're going to have to solve for x when 3 equals to -x squared plus 4x. Okay, well, luckily we can easily solve this one. We can factor out that -x again. 3 equals to -x times, and we have x. Oops, what am I doing? We want to move this guy over, minus it over to the other side, so we get -3 minus 3, we get 0. 0 equals to -x squared plus 4x minus 3. Let's factor out that -1 times, and then x squared minus 4x plus 3. Okay, so we can factor that guy out. -3 times -1 equals +3. And then -3 plus -1 adds up to -4. So this is going to be -1 times x minus 3, x minus 1. Right, this thing foils into this one. And now we have the zero product principle. That means that x minus 3 equals 0, or x minus 1 equals 0. Therefore, x equals to 3 is one solution, and x equals to 1 is another solution. And well, 1 we had already guessed, and 3 I just guessed in the graph, and it also works out nicely. So that's how we can confirm that this value right here is a 1, and that if we come down here, that this value right here is a 3. Okay, so the online program needed to know these two values, and that's why it has this little region right in here is what needs to be rotated. Any questions right now? Is everyone with me? right? We're going to take this, and this is what gets rotated around the x equals to 1 kind of pole there. Okay.
Okay, yeah, I do have a quick question.
Yeah.
So we have to find the 3 on the x-axis before we can determine the complete region for rotation?
For the computer program, yes. Because if you go over here, you need to type this in, because if you don't type it in, it'll rotate something else, right? So like, for example, if this was just a random 5 in there. Come on. Oh, man. There. See how if there's a 5 in there, it's not going to do just this part, and look at how ugly my final result is, right? So we don't want that. We want just the little region bounded by these 2 curves, which is this, which means you have to figure out when it intercepts. So for that purpose, you definitely need it. And now as far as the work that you're going to show, when you're doing this, the reason you might need it is because when we set up our integral to actually find the volume, it might be important to know where x is going. X is ranging from this little region right in here from 1 to 3. Okay? And also, when we set it up, we might need to know where y is going, and y is going from 3 to 4.
Okay, I just was wondering because I've been plotting the x equals 1, just graphing it as the function, and that usually helps give me the constraint or the limit where it crosses the other function, but I didn't think about the 3. So thank you for explaining that. Didn't think about that. So.
Okay, cool. Right, so when we set up our final integral, we're going to need to know these things. What should I put it as? Let's put it in all right, so the x is ranging from 1 to 3, and the y, here's our y, it's going from 3 to 4. And so this right here is our y. Our y is going from 3 to, I don't like that. Squeezing it in too much. Right here. And so y is going from 3 less than or equal to y less than or equal to 4. This is this little zone right there. Okay, so back to the computer program. Let's see if it does a good job of doing this thing. Okay, so we found the region. The last thing we need to do is tell it where to rotate this. So we want to rotate it around the line x equals to 1. And there you go. That's what it looks like. Right, so kind of like, I was trying to draw it in this direction. Well, actually, I guess, come on. It's kind of hard to control this thing. Come on. Rotate. Come on. Okay, well, we're gonna have to give up. I can't rotate it the way I want it to rotate it. So, no, don't do that. Anyway, it's kind of like this, except notice that the x-axis positive direction is this way, and the negative direction is going that way. I would ideally like to see it the other way, but it's kind of hard to manipulate it. Whoa, did that do it? Oh, there we go. No. There we go. Okay, so positive x direction this way, negative x direction that way, and here is our result when we rotate it, right? So here's that parabola right there, and then it rotates and it gives you this sort of a shape thing. Come on. It won't twist in the other direction now. Okay, well, this is a good direct. You know what? I might need this in a second, so let me take a picture of this thing, and then I'll move out. Okay, but this is a better way to see the actual thing. Okay, so now we're doing this by the method of shells. So let's see if I can highlight a shell. Does it look better if I do this? So there's one shell, right there. And as I go through it, as I go through my little section, we see the different kinds of shells that we're going to get. Right? Remember that there's going to be a little thickness to them, and that little thickness is going to be that dx. Right? If I take one shell and I slice it, I cut it, and I roll it all out, I'm going to get something that looks like a sheet. And that sheet is going to have a little thickness, which is equal to the thickness of this shell. And so that'll be the dx. Now, the height of that shell, the height is going to be equal to this height right here. Good? So the distance between the line y equals to 3 and the top of my parabola, that's going to be the height of this thing. And then the last thing I need is how long is it going to be, and the length of it is the perimeter of this shell. I need that picture as well. Good. The one thing I'm unhappy about this graph is that it doesn't really show the thickness of this. So remember that it's a little bit, it's got some width to it. It's got some thickness to it. When we're only applying a small number, when dx is, some delta x is, when delta x is got some value, it's only going to become infinitely thin as we let n go out to infinity. That makes sense? Kind of, maybe. Let me see if I increase this a little bit. Okay, about 10. Okay, there we see that if we have 10 different ones, as we kind of rotate from the center out to the outer one, all of these different cylindrical shells will begin to form the shape that we're interested in. Good. Right, for every one of these shells, it's almost like a cylinder with a hole through the center of it. The height of each one of these shells is determined by this. And then we rotate all the way around, so we need the perimeter of it. And the perimeter is going to need a radius. The radius is going to be based on where we're rotating. We're rotating from here. This is the axis of rotation. So for the particular shell I'm highlighting right now, this yellow one, the radius is going to be the distance from here to there, right? And then it'll rotate. Good? Good. Okay, so now let's try and set up an integral that will solve that for us. I need some nice pictures. Come on. Well, this image blows that out of the water. Let's put this over here. Let's put that over there. And then this one. Okay, so between these three images, I should be able to figure out the setup that I need. Okay, so here's this parabola. That's this parabola right here from this perspective is right here. And then this is the line x equals to 1, right? That line. And we're rotating it this way around that line. X equals to 1. Rotating it. And then we get this sort of bun cake kind of shape kind of thing. So if we slice into it from this perspective, we slice into it, we're going to get this sort of a shape as a cross-sectional area when we slice into it, right? Okay, so we want shells. The shells are going to look a little like this, except they have some sort of thickness to them. And we want to be able to use our formula that it's going to be volume of one shell, volume of one shell, cylindrical shell, is going to be equal to the thickness of it. I want that thickness, which for us is going to be a delta x. Remember, the way we're slicing into this, think of it like a knife coming down from the top down and going around it, right? So like there's this knife that kind of comes from the top of here, right there, and it slices all the way around. Oops, that was almost good, and then I blew it. Come on. So we're going to come down from the top of this, and we're going to slice from the top down. I'm going to slice this way and go all the way around. And then we're going to come back again and cut right next to it, and then slice all the way around again, so that we have a little thickness to this thing. There's going to be a little thickness to it. And then it goes all the way down deep into the base of our cake. Okay, so we'll end up with a cylindrical shell. Now the thickness of it has to do with the dx. We came down here, and it's going to be this, right? There's going to be a little piece of it that we cut, and so this is going to be the thickness of it. So looking at it from this perspective, if my knife came down this way, like this, and like penetrated it there, and then created a little this that way, and then I came at it again and penetrated it this way, and so there's this little thing here, there's a little thickness to it, and it comes down all the way down, right? So this is the shell that comes down. So then the thickness of it is going to be this. And that's going to be a delta x because it's along the x-axis. Good? Okay, so that's the thickness of it. Now, besides the thickness of it, the height, if I took out that yellow, this guy, if I took it out and rolled it all out, I would have that right there. Let's say that is this. And then the rest of it would roll out. I don't know if yellow is going to look very good here. But it would roll out into something that comes this way. Is the yellow okay? Can you see the yellow? Is it hard to see yellow? There. Sort of. It's one big rectangle, right? If I cut it there and rolled it out, it's got a little thickness to it. Go back to this thing. It's got a little thickness to it. And that thickness is going to be that delta x. And then the length of it, this length is going to be equal to the circumference of the circle. Good? Circumference. And then the height is going to be equal to this height. Let's put it in a different color. This red right here is kind of like this red right there, and this is going to be the height between the difference between this function, the parabola, and the line. Okay, so it's really equal to the parabola value minus the 3. Okay, so this is the height, and this is the circumference. Okay, so the volume of one shell is going to be equal to the thickness times the circumference times the height. thickness, volume of one shell is equal to the thickness times the height times the length. And so for us, that thickness is going to be the delta x. The height of it is going to be equal to the function, which is minus x squared plus 4x. That's the parabola minus the 3. And then that'll give you this, right? Because remember that this right here is the line y equals to 3 is this guy. And minus x squared plus 4x is the parabola. So that height right there is this one minus that one. And it's a y value, so you input an x coordinate, and the output is going to be this y value for this equation minus this y value. Right? So this together will be the height. And then we need the length of this yellow guy here, and it looks really ugly, so maybe I should just put that in there. We need the circumference. The length for us will be the circumference. And the circumference, well, we need the radius. And the radius is going to be equal to, let's go back to this picture. We said that the radius for each one of these guys is going to be equal to the distance between this point, say here and here. It's going to be where it rotates. So it's going to be the y value result minus the 1 is going to give you, the value of x rotated around, so the distance between here and that point along the x-axis. So if this is the outer edge of the shell, it's going to extend out to here. So we need this distance. From here to here is the radius of rotation, right, for this particular shell. And if the shell was smaller, if we went over here, it would be the distance from 1 out to there. So how do we find that distance? It's going to be the x coordinate of where you decided to, cut your shell minus 1. Did that make sense? I'm not sure if that's the best explanation. Going into this thing. Whoa.
So just be the radius would just be x if we weren't rotating it about x equals 1, right?
Correct.
Just by the origin. All right.
Correct. Okay, so the radius is going to be equal to 1 minus x. Oh, the other way around. X minus 1. X minus 1. Good. Yeah, that's not a great picture to look at that from. I guess this is probably the best one to look at. For one shell, when we have one shell coming down into this thing, we're going to have a little section here cut off, and then this is the section that gets rotated around. So we'll end up with something like, whoa, that's something. We'll end up with something this way, and even other than that. Why can't I get it straight? It's really hard to write with this thing. Whatever. Okay, so we end up with a cylinder that looks like this, and then the radius we approximate it to be equal to this. So here's our x value that we put in. And then the distance between these two, where this is 1, so x minus 1 will tell you the distance from there to there, which will be our radius. And the formula for the circumference of any circle is 2 pi r. So the circumference is going to be equal to 2 pi times the radius or just 2 pi times x minus 1. Okay, well, that was really messy. Let's actually write down the integral now. So now we're ready to set up the integral. So the volume is going to be equal to this integral. I like to jump ahead and think about where my dx is or my dy, depending on how you cut it. In this case, it's going to be a dx, so I can organize things. So I know that this needs to be written in terms of x. Okay, so that's kind of a nice hint. I need the radius, the circumference, so that's going to be 2 pi x minus 1. That'll give you the circumference, times, and then I need the height, and the height is equal to this thing. So the height is going to be equal to minus x squared. I need to make some space here. Minus x squared plus 4 minus 3. That'll give you that. And then it's thickness, which gives you that. And then we're looking at x, and so x ranges from, and looking at my picture, it went from 1 to 3. So there's the setup. That's the hardest part of this section, figuring out the setup for your integral. Once you have it at this point, then it's really a matter of solving the integral, which hopefully isn't too difficult. Right? Hopefully they don't give you something that's too difficult to figure out. Okay, so then let's just simplify that. We can take out the 2 pi out in front, since that's just a constant. Integral of from 1 to 3. And then I have this x minus 1 times minus x squared plus 4, oops, this is 4x. 4x minus 3 dx. That's equal to my volume. So I'm just going to FOIL this guy out. That'll give me a nice, pretty polynomial. X cubed minus x cubed plus 4x squared minus 3x plus x squared minus 4x plus 3. We FOIL that whole thing out, and then we'll still have our dx, and then we still want to integrate from 1 to 3, and we have 2x there. Combining some like terms, we get that this is equal to, that this is 2 pi integral from 1 to 3. Nobody wants to play with the x cubed, and then the x squared and the x squared, that equals to plus 5x squared. And then nobody, okay, so then minus 7x plus 3 dx. That's my volume. And then these are nice, easy polynomials. So minus 1/4, come on. One-fourth x to the 4th plus 5 times 1/3 x to the 3rd minus 7 1/2 x squared plus 3x. Evaluate it from 1 to 3, and they match, so we don't. I dropped the notation of x equals 2 on the limits of integration since they all match. Be careful with that when they don't match. If all of a sudden you did like a substitution or something, then you have to be careful about the limits, the variable of integration. Okay, so now this is easy.
And the 3 doesn't have an x at the end of that last.
3 does not have an x.
7.5x squared plus 3x is just 3 on the next line over.
Oh, so after I find the antiderivative, right, the derivative of 3x is 3. Is that what you were saying?
But yeah, my fault. I forget about, no, that was my mistake. I always forget the antiderivative.
Oh, okay.
My fault. Sorry.
Cool. No, that's fine. Thanks for letting me know. I make
always
mistakes.
forget that. Sorry.
No worries. Okay, so there's different ways to set this up. It can get a little messy. So one way to set it up is just to think of all the ones with a 3. So let's put that plus 5/3 this cubed minus 7/2 this squared plus 3 times something. Okay, so that minus, and then do it again, minus 1/4 something to the 4th plus 5/3 something to the 3rd minus 7/2 something squared plus 3 times I hate computers, times something, and then all of that of course gets multiplied by the 2 pi, so there. Be careful to distribute this minus across everything. So here we have 3, so 3 to the 4th, 3 to the 3rd, 3 squared, 3 times 3. And here we have 1, 1, 1, and 1. So we just have to do a little bit of arithmetic here. 3 to the 4th is equal to 81, so that'll be 2 pi, bracket, that's going to be negative 81/4, plus 3 to the 3rd is 27. 27 times 5 is equal to 110, I think. 27 times 5. Oh, nope, I was wrong. 135. 135/3 minus 9 times 7. That's going to be minus 63/2 plus 9 minus, so minus wrong all these signs, maybe it's messing up.
6 times 7. I think you put 63 on the bottom line, but shouldn't that be 42?
Oh, where is it? 6 times 7 is 40.
The last line where you have minus 20 plus 63, that should be 42.
Well, if you want to do algebra, right? Yes. Sorry, 42. Okay, does that give me the answer I need? Negative 243 plus 540 minus 378 plus 108 plus 3 minus 20 plus 42 minus 36. We get the 16. Cool. Okay, so that's going to bring us over to 16. And then that reduces into 8/3. Yes, 8 pi over 3. 2 goes into there, 2 goes into there, and that's our answer. Volume. So this whole side over here is just volume. Okay, any questions about the actual solving of things here? Just don't do what I did. Be careful, meticulous. It always helps to know what the final answer is, just so that you can go back and make sure that little arithmetic things So the back of the book should have all the answers, so that's nice to at least confirm what the answer should be. Good, good. Any more questions on this one? We can do a better job of pointing out that the radius is the distance from there to there, which is the x-axis value, the x-axis value, which is x minus the 1. Don't rotate anymore. Come on. Oh, whatever. The distance between here to there. So like the yellow one that's being identified right now, it's got a little thickness of dx, and then the radius would be from there to there, right? Which is x minus 1. Okay, any more questions on this one? Setting up is the hardest part. So try and come up with, a sense of what it looks like, an image. Do your best, and set up the integral at least. Okay, so if there's no more questions on this one, are there any other questions?
Um, 6.2, you asked us to set up the problem but not to solve it.
Yeah.
But would you be willing to do number 19 just to solve it? Or would that take too much time?
I don't know. I don't know what number 19. It could potentially be something that takes a really long time. So I separated it because very often the issue or the problem with finding the integral can be really hard, right? As we saw in chapter 7, it sometimes takes a lot of work to figure out the integral. So I wanted to separate that skill of finding difficult integrals, separate that from the current chapter, which is really about visualizing the shape and setting up the integral. When the exam comes, I might do the same thing for at least a couple of questions where I just ask you to set it up, and the setup might result in a really ugly integral. But you would just stop there, just set it up as long as you know what you need to solve, right? Step 1 is to figure out which integral you need to solve, and then solve it. Sometimes assigning a bunch of problems where you do the whole thing from beginning to end becomes very repetitive because the actual integrals aren't that bad. A lot of them end up being like little polynomials like this one. It just becomes kind of tedious. Whereas sometimes the integral might be really, 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 really hard, maybe even impossible to solve, right? Don't fall under the assumption that we can solve anything. It's not true. There's many integrals that we just don't know how to solve. And sometimes we just don't have a solution, and often we settle on an approximation. Often we use computers to approximate the answer. So to readdress your question again, I mean, I'd be willing to look at it, but the setup is the most important part. It's important to be able to know how to set it up. And once you've set it up, then that integral almost always ends up being a simple integral to solve in this chapter. If not, you might have to rely on some of our other techniques from before to figure out how to set it up. Okay, so having said all that, let's take a look at it. Where is it? You said this was section 6.2?
Yeah, 6.2, number 19, please. if time allows. If not, that's fine.
That's okay. Okay, so 6.2, number 19. So we're given this little image here, and so it says region R sub 1. So that's this blue region. The blue region rotated about the line OA. OA is the x-axis, right? So we're going to rotate this around, and when we do that, we're going to get something that's like a cone, very sharp cone that comes up to this little point right there, and it has that sort of cone. So let me copy this down. Okay, so here's our graph. Here's this thing. And where did this guy go? Okay, so number 19. Let's go here. This is going to be Chapter 2, Section 2, number 19. Okay, so refer to the figure, volume, generated given the region, specified about the line. Okay, so region 1, about the line OA. Okay, so we want to rotate about this line OA. Whoops. This line right here. Well, what does that line go by? Oh man, I hate these things. I'm just trying to do a simple line here. Alright, let's make it thicker. Maybe that'll make it easier. Can't go straight to save my life. Almost. Okay, we're going to pretend that's good enough. Alright. We want to rotate around there. So if we rotate around there, go this way, around the, well, it's the x-axis, right? So another way of defining this rotation is to rotate about the x-axis. Rotate about OA is the same as rotate about the x-axis, which is the same as saying rotate about the line y equals to 0. Right? Y equals to 0 is the x-axis. And when you do that, you're going to end up with something that's got a circular base, a big circular base over here. Big circular base that comes down to a sharp point. That comes this way, like that. Good. And then there's this thing right there, which is the line y equals to 0, or the x-axis, and rotates around there. Okay, so we're going to do this by the method of coins. We're going to come in here, and we're going to cut a coin from here like this. We're going to cut into it this way. So it's going to have something like this. It's going to have a little thickness to it, which is going to be that delta x. And what am I doing here? The radius, yeah, so if I cut into it, so this is going to be something that comes into here like this. Oh, that's really ugly. Got a little thickness to it. delta x. So the radius of this thing is going to be the distance from the x-axis up to there. That's going to be the radius. Y is the radius. And the y is the distance from there to there. Now we have the point 0, 0 there. And we have the point 1, 1 there. So if you want to find this little blue line, that blue line is going to be a straight line that has a slope. So let's say equation of the blue line. Of that blue line is the line that goes through the point 0, 0 and 1, 1. So we need the slope. Well, the slope is going to be 1 minus 1 minus 0 over 1 minus 0. So it's going to be 1. It's got a slope of 1. And it's got a y-intercept of 0. So the line is going to be equal to 1 times x plus 0, or just the line y equals to x, right? So this line right here is the line y equals x. Good, 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 good. Okay, so when we choose an x value along here for my slice, for my coin, then the radius is going to be equal to this guy right here, which is equivalent, it's this relationship. Good. So this guy is my radius. Okay. So I want my integral for my volume. Volume is going to be an integral, and I'm chopping it with little dx's, right? So I like to put that out there first. I want my equation here to be written in dx. And it's going to be equal to the pi r squared formula, right? Pi times radius squared. And x is going to range from 0 to 1. X goes from 0 to 1. And then that radius, I said, is this thing here. And so the radius is governed by this relationship, the y equals to x. So you can use either one, the y or the x, and it would be true that that's what gives you the value of the radius. But I want it in terms of x. So my volume is going to be the integral from 0 to 1 of pi x squared dx. Luckily, that's a really simple integral to solve. So my volume is going to be equal to pi 1/3 x cubed evaluated from 0 to 1, which is going to be equal to pi times, well, it's pi over 3, and it's going to be 1 cubed minus 0 cubed, which is just going to be 1, and so this is just going to be pi over 3. So that's our volume, pi over 3. Good. Questions?
No, thank you. I appreciate that. That helped a lot.
Good. Sorry for my terrible drawing. It's more terrible than normal.
It's discernible. I can tell what you're trying to draw there. Makes sense.
Oh, good. As long as we have this guy over here, well, I can do a better job of this. So let's try doing it with this guy. We have the line y equals to x, and y equals to x and the line 0. Let's do that. And we want to go from starting at 0, going out to 1. And let's zoom into here. Okay, so we'd have to do a little bit of work to put it in here because we needed to solve for that line of y equals to x, and that would be this line. And then the other one, the computer program also wants another function so that we trap them between them. So it's going to be the line y equals to 0, so that's this one. And then we want to go from 0 to 1. So once we set all that up, we have our nice little triangular area. And we want to rotate along the line y equals to 0, so that looks good. And then when we rotate, we'll end up with something that looks like this. So it's like a very sharp cone-looking thing. And then we're going to slice along the x-axis, right? So as we slice along the x-axis, we end up with coins, right? So here's that yellow coin right there. Zoom in a little more. Whoa, too much. So here's that yellow coin. As I slice through it, sometimes it's a really big, thick, well, the thickness stays the same, but it's a really big coin sometimes. And it's cutting off the edge of this picture here. Stop it. All right, let's go a little bit more. There. So sometimes it's a fairly large coin, and then as I slice way over here, closer to the tip, it's going to be a much smaller coin, a tiny little coin. Okay, so just for one sort of general one somewhere in the middle over here, we're going to have a thickness. The thickness is going to be a delta x, the thickness of this coin. And so if we multiply the area of the yellow times the thickness, that'll give us the volume of the coin. The area of the yellow is going to be the radius. The radius is going to be this squared, radius squared times radius squared times pi. And since the relationship is y equals to x, then that's how we get our integral. Yeah. Get a nice image of this thing around there. So the radius, right? So notice that this is the x-axis this way, this is the y-axis going that way. So on the floor of this is this triangle. And so the radius is from there to there. That's the radius. And so we need to figure out that relationship, and the relationship there is given by the equation y equals to x. And so that's how we establish that that's what the radius is going to be. Good. The radius there. So you might be thinking, why not put the y there? That's fine. If you do this, it's technically correct. If you did pi y squared dx, sure, but we're integrating with respect to x. So that's just causing problems, right? So this relationship is the relationship between x and y in that radius, so you can use either one. So often I like to write down the equation that governs that, and then I choose whether I want it to be written in terms of y, because I have a dy over here, or x, if I have a dx. Good. So in other problems, this might end up being a more complicated relationship, right? You might have something like x squared plus 1 equals to 2x minus 7. That might be the relationship that describes the radius of something, and then you'd have to solve for x when you plug it in there, or maybe think about solving for y if you have a dy. Okay. Any other questions on this one?
No, thank you.
Good. Okay.
That helps a lot. Thank you.
No problem. Okay, so let's stop there for now then. So please continue to work on Chapter 6 and let me know if you have trouble with anything. Send me an email if you want to meet and go over anything. Otherwise, our test is next week on the 22nd, and it only covers Chapter 6. Right? So as you pointed out with this question, there could be the exam will mirror your homework, so there could be questions on the exam that just ask you to set it up and not solve it. In this case, it was actually really easy to solve it, but it just takes more time. So once you get to a point where the integral has been set up, the rest is just, you good? Good? All right. I will see you Thursday then. Have a good day.
Thank you, Professor. You too.